So we're going to wrap up this section by talking a little bit more about Pascal's triangle and the interesting patterns we see there. So remember, this was Pascal's triangle that we talked about in the last video. We had seen that row n will show you all of the subsets of a particular size of an n element set. So for example, this is row 4, and it shows you 4 choose 0, the number of subsets of a 4 element set of size 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And this seems to be the case in general. So another interesting thing to notice, beyond the fact that it's symmetric, which is what we talked about in the last video, is the fact that the elements of a particular row can show you something interesting about the binomial a plus b raised to a particular power. So let's consider for a second the term, or the binomial a plus b raised to the 5th power. Remember, that means a plus b times a plus b times a plus b, 5 copies of a plus b multiplied together. And if we wanted to actually multiply that all out, I won't make you do it because it's messy, you need to distribute 4 times and it gets to be this really long thing. But once you simplify, you get this expression right here. Okay, a to the 5th plus 5, a to the 4th b, all the way down the line. Now the interesting thing to notice here is that if you look at the coefficients, right, we can assume there's a coefficient of a 1 here and a 1 here. Pulling out the coefficients gives us 1, 5, 10, 10, 5, and 1. That should look familiar. That's the 5th row of Pascal's triangle. Oops, not here, here. Right, 1, 5, 10, 10, 5, and 1 is the 5th row of Pascal's triangle. And we know that this is really the same as 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, etc. Which means another way of rewriting this expanded out binomial a plus b to the 5th power is we can say that this is like having 5 choose 0 times a to the 5th power plus 5 choose 1 times a to the 4th b plus 5 choose 2, a cubed b squared, plus 5 choose 3, a squared b cubed, plus 5 choose 4, a b to the 4th, plus 5 choose 5 times b to the 5. Okay. What did we notice here about these coefficients? Well, the number at the bottom, the thing that you're choosing, seems to match the exponent on the b term. 5 choose 1, a to the 4th, b to the 1. 5 choose 2, a to the 3rd, b to the 2. 5 choose 3, a squared, b to the 3rd, etc. And this can be a really handy way, if this is true in general, of expanding out a binomial raised to a particular power. It comes up all the time in probability, comes up in many different contexts as well. This suggests to us that in general, a plus b to the nth power can be given by this formula right here. This, in fact, this result is called the binomial theorem. It says that if n is a natural number, then a plus b to the nth power is given by the following formula. Right, so you start with an a to the nth power, you have n choose 0 copies of that. Then a to the n minus 1 times b to the 1, and you have n choose 1 copies of that, all the way down the line. This is going to come in really handy. This is a very important result. Okay, so why is this the case in general? It can be helpful to look at a smaller example to see why this is happening. Why the coefficients, when you expand out a plus b to the n, why the coefficients end up being these n choose somethings, right? These combinations of n choose something. So let's see if we can figure that out using a specific example. I'm going to look at a plus b to the 3rd power. Remember, a plus b to the 3rd power just means 3 copies of a plus b multiplied together. And when we expand it all out, you get a cubed plus 3a squared b plus 3ab squared plus b cubed. And this matches with what we saw in Pascal's triangle. The 3rd row had 1, 3, 3, and 1. And the coefficients here again are 1, 3, 3, and 1. Right, so this suggests to us, based on what we saw before, that we could rewrite this as 3 choose 0, a to the 3rd, plus 3 choose 1, a squared b, plus 3 choose 2, ab squared, plus 3 choose 3b cubed. Right, that's what seems like it's going to be true, but why is that the case? Well, if we think about what happens when we try to expand out a plus b to the third power, it means a plus b, a plus b, a plus b, but for our purposes, it's going to be helpful to sort of distinguish between each set, right, between each of these binomials that we're multiplying together. So I'm going to kind of group them together and say the first binomial is a1 plus b1, the second binomial is a2 plus b2, and the third binomial is a3 plus b3. Every term, when we expand this out, is going to have one term chosen from the first set of parentheses, one term chosen from the second set of parentheses, and one term chosen from the third set of parentheses. Right? So you'll get, for instance, you use a different color here, you'll get, a1, a2, a3, right, if you multiply each of the a's together. But you could also choose a1, a2, and b3. Or you could choose a1, b2, a3. Right? You could choose a's from the first and the third, but a b from the second. Or you could choose b1, a2, a3. So you go through and try to pick out every different possible way you could choose one term from the first set of parentheses, one term from the second set, and one term from the third. So far, I've covered the cases where I chose all A's, then the case where I chose two A's and a B. Now I need to cover the case where I choose two B's and an A. So, for instance, you could have B1, B2, A3, or you could have B1, A2, B3, or you could have A1, B2, B3. Or finally, the last thing you could choose is you could choose all three B's, right? B1, B2, B3. Now I've distinguished them up here just so that we can sort of see where this is coming from, but really all these A's are the same, right? It's really just A. Each of these A's is equal to A. So in the end, you end up with A1, A2, A3. That's your A cubed. Now how many copies of A squared B do you have? You get one here, and one here. Well, you get 3 copies of A squared B. But why is it 3 copies? Well, there were 3 different ways that we could choose 2 of our sets of parentheses to pick the A from, and then 1 set of parentheses to pick the B from. Or another way of saying that is to say, look at your 3 different sets of parentheses, choose which of those 3 you're going to choose a B from. Right, there's 3 choose 1 many ways to choose 1 set of parentheses as your B term, and then choose A's from the other 2 sets of parentheses. Right? Similarly, if we wanted to look at our A, B squared terms, that would be here, here, and here. In this case, we want to choose 2 out of the 3 sets of parentheses to choose a B term from. How many ways can you choose 2 sets of parentheses out of 3? Well, there's 3 choose 2 many ways. And finally, there's 3 choose 3 many ways to choose B from every single set of parentheses. Right? We can think about this as 3 choose 0 because we didn't choose any sets of parentheses to choose a B from. Okay? So we kind of see now where this is coming from, where we're getting these binomial coefficients or these combinations. It's because each term in general, when we expand A plus B to the nth power, the term, let's say A to the k, B to the n minus k, will have a coefficient of n choose n minus k. And the reason for that is that when we expand out this expression, A plus B to the n, we have n many copies of A plus B. Each term of the form a to the k, b to the n minus k is formed by choosing n minus k sets of parentheses to pick a b term from, and then making sure that you chose a's from all of the other sets of parentheses. The number of ways that you can choose n minus k b's from within the choice of n b's would be n choose n minus k. All right, so this is a really important result. Sometimes it's also written as follows. Sometimes it's written as a plus b to the n is equal to the sum where k goes from 0 to n of n choose n minus k, a to the k, b to the n minus k. Sometimes this is even replaced here with just a k, because we've seen that it's symmetric and you'll get the same thing either way. But this is what we call the binomial theorem. And in the exercises, we'll explore it a little more and see if we can find some interesting results that come from this.